Welcome all. So, today we will be dealing with the multiple degree of freedom system analysis for the structures subjected to blast loading. In the previous classes, we have seen the MDOF analysis to the impact loading. So, continuing from that, in this week we will be looking into the analysis of the structural elements subjected to blast loading. So, let us start the course. So, the different categories of structural response to blast loading. Okay. So, structural elements can be grouped into three response ranges. Okay. So, primarily we can group them into three ranges, okay, depending upon how they react to the dynamic loading. Okay. So, we can group them into the low pressure range, intermediate pressure range and the high pressure range. Okay. So, what happens in the low pressure range? Okay. So, in the low pressure range, the element responds primarily to the magnitude of the pressure. Okay. So, the interaction between the time dependency of the loading and the time period of the structure is minimal. Okay. So, basically it is acting as a pseudo static loading. Okay. So, in the low pressure range, the response is primarily governed by the magnitude of the pressure. Okay. So, here the time dependence is less significant. Okay. So, earlier we have seen any response, okay, will be a function of the interaction between the structural properties. Okay. Structural properties we can denote by time period, the time of the loading Td and the magnitude of the loading. Okay. So, in the low plastic range, okay, the dependency on the time is minimal. Okay. So, primarily we can approximate this thing using a function for the loading only. Okay. So, the primary response is due to the magnitude of the pressure. Okay. Next comes the intermediate pressure range. So, in the intermediate pressure range, elements respond to the pressure time relationship, okay, that is varying the loading with respect to time. Okay. So, in this relationship, y becomes primarily a function of pressure as well as the time, how the loading is changing. Okay. Its dependency on the structural response is minimum. Okay. In the high pressure range, the third is the high pressure range. So, in the high pressure range, elements will respond to the impulse, that is the integral of pressure over time, that is the total energy delivered. Okay. So, now y is becoming a function of the structural response as well as the integral of pressure time curve. Okay. So, if this is the pressure time curve, okay, for a blast, if this is the pressure time curve, the response is governed by the total impulse energy. Okay. So, the integral of this pressure time curve, okay, will be responsible for the response of the system in addition to the structural response. Okay. So, this is how the response of the system depends upon the three conditions. In the low pressure range, it is entirely dependent upon the magnitude of the loading, that is the magnitude of pressure. In the intermediate pressure range, it is dependent upon the pressure time relationship, how the pressure is varying with respect to the time, and in high pressure range, it depends upon the sum total of the energy given to the imparted to the system. Okay. So, what are the different methods of analysis? Okay. So, there are different methods are used depending upon which group the element belongs to, whether the element belongs to the low pressure range, the intermediate pressure range or the high pressure range. Okay. So, depending upon the grouping, we can apply different pressure time responses depending upon their accuracy. Okay. So, pressure only or pressure time responses, okay, that is, it means that it belongs to group 1 and 2, the low pressure group and the intermediate pressure group. Okay. So, here we can use the analysis methods, okay, like numerical method, we can use the step by step integration, which is suitable for the complex case, or we can use the simplified design charts. Okay. And if it belongs to the impulse response, that is the group 3, okay, here this is belonging to the group 3. So, here we can use the design charts for large deflections, okay, or we can use the impulse method. Okay. So, depending upon which group the loading is subjected to, okay, we can analyze using different methods, numerical methods, design charts. Okay. So, these are the simplified design charts, or if it is belonging to the high pressure range, we can use the design charts for the large deflections, or you can use the impulse method. Okay. So, continuing with this. Okay. So, what are the different numerical methods? Numerical methods are general and can handle any type of load or resistance behavior. Okay. So, we have different types of numerical method and they are generic in sense and they can be used for any type of loading or any type of structural configuration. Okay. The numerical method rely on step by step integration. Okay. They follow the marching in time. Okay. It means that we are integrating step by step with respect to the time. Okay. Simulating how the structure responds over time. So, this is what we call as the marching in time or step integration with respect to the time. Okay. Design charts. Okay. So, there are other class of solutions available. Okay. They are known as the design charts. So, basically what happens in the design chart is that depending upon the structural configuration, the period of the loading and the magnitude of the loading, okay, whether it be it in the elastic range or whether it be it in the plastic range, we have developed or we can develop the responses. Okay. So, we can, for example, we can have this type of design charts. Okay. So, all this numbers corresponds to RU over P value. Okay. And here this is Y dynamic, Y static, and this will T over T G. Okay. And let us say this is for this type of loading. Okay. So, in design charts what is happening are these are the charts developed from systematic study of single degree of freedom systems under idealized loading. Okay. And then the results are expressed in non-dimensional form, making them applicable to many cases without recalculating from scratch. Okay. What does it mean is that let us say we have any structural system. Okay. Let us say we have a beam. Okay. Or we can have a column. Okay. Or we can have a plate. Okay. Supported on any sides. Okay. So, what we can do is that we can approximate all this system using a single degree of freedom response. Okay. So, we can approximate this system using an SDF system, okay, with certain load applied. Okay. So, from here what we can do is that we can calculate the response of the system subjected to this pressure load. We can calculate the response of the system. Okay. We can calculate the Y. Okay. So, now Y is a function of the structural properties M and K. Okay. So, this M and K combined we can represent using the time period of the structure. Then this response is also a function of the loading, that is P, and this is also a function of the time of the loading. Okay. Let us say Td, or if it is expressed like this Td. So, this is also a function of the loading duration. Okay. In addition to that, okay, the response is also a function of whether the structure is in the elastic range or whether it has gone into elastoplastic range or whether it has gone completely into the plastic range. Okay. So, that representation we are denoting by Ru over P. Okay. That is the resistance of the system to the applied loading. Okay. So, this is how my response will look like. Okay. It will be a function of the system, it will be a function of the magnitude of the loading, it will be a function of the time period of the loading, and it will be a function of whether the structure is in the elastic range, elastoplastic range, or in the plastic range. Okay. So, now this is the representation that we are using. So, Y dynamic we can normalize using Y static. Okay. So, this thing we are plotting in the Y axis. In x axis we are plotting a ratio of the time period of the structure to the time of the loading. Okay. Tn over Td. Okay. And we are using different curves, okay, denoting whether my structure is in the elastic range, elastoplastic range, or whatever range is that. Okay. And P is the magnitude of the loading. Okay. So, P will be inside the Y static loading. Okay. So, for any structure we will note the time period of the structure, we will know the time of the loading, okay, and we will know the resistance of the structure, and we will know the applied loading. Okay. So, all these 4 factors will be known. Okay. So, we can read from the x axis, we got the y axis value. Okay. So, we got the y dynamic over y static. Okay. So, we will get this number. Okay. So, if I multiply over y static, okay, so y static is nothing but P over K, okay, the loading divided by the stiffness. Okay. So, directly I can calculate my y dynamic. Okay. So, without doing the rigorous calculation from the scratch, okay, using this design charts, okay, using this pre-developed design chart, we can calculate the response of our system. Okay. So, element which responds to pressure only and pressure time relationship. Okay. So, the requirement for analysis. Okay. To analyze structural elements under blast load, one must know the two pressure time relationship. Okay. how pressure varies with time during the blast. It means that what we need to know is that we are supposed to know the Friedlander curve. Okay. So, this is we have already discussed, this is the Friedlander curve. Okay. So, this is how the blast wave behaves. Okay. So, this is the pressure time relationship, okay, and this is the true pressure time relationship. Okay. The dynamic response of the element depends upon how its properties interacts with this blast input. So, this is the blast input. Okay. So, this is the blast input or blast signature, and this is called as the Friedlander's profile. Okay. So, this is called the Friedlander's profile. Okay. The properties of the structure. Okay. So, properties of the structure, one basic property is the natural period of vibration, that is the Tn, okay, which is again a function of mass, stiffness, and damping also, whether we are considering damping or we are not considering damping. Okay. So, if there is no damping, it becomes a time period of the undamped system, or if damping is considered, then it becomes the damped period of vibration. Okay. Basically, how quickly it oscillates on its own. Okay. Then the resistance. Okay. This is the strength against the applied forces. Basically, there will be Ru. Okay. What it means is that if, let us say, we have a beam out here, okay, and it is deflected under application of the blast loading. Okay. So, if you look into the cross section, if you cut it and if you are looking into the cross section of this beam, what will happen is that if this is the case, okay, so in this case the top part will go under compression, the bottom part will be under tension. Okay. So, this is how the system is going to behave. Okay. So, if the magnitude of the loading increases, okay, this value of strain will keep on increasing. Okay. So, there will be certain point, okay, where the strain value will exceeds its yield value. Okay. So, after that, here the strain might be less than the elastic strain. Okay. So, there will, depending upon the loading, okay, this strain might exceed the elastic strain. Okay. So, once this happens, the other fibers will also start to yield. Okay. So, this is the resistance function, okay, and depending upon the loading, okay, different type of scenarios might occur. Okay. So, this is the system condition. Okay. So, the response also depends upon the ratio of the resistance to the applied loading, okay, whether system is in purely elastic range, whether the system is in elastoplastic range, or whether the system has gone into the pure plastic range. Okay. So, that will be determined by the ratio of the resistance to pressure. Okay. So, this is the thing. Okay. And then of course, deflection, how much it bends or displaces. Okay. So, these are the parameters on which the response of the system is going to depend. Okay. Moving ahead. So, numerical method of analysis. So, what we do in the numerical method of analysis, we have seen what we are doing in the design chart. Okay. So, now we will see what we are doing in the numerical method of analysis. Okay. So, the principle. So, the response is calculated by step integration in time. Okay. So, what we know as the marching in time. Okay. So, what we do is that we evaluate the response of the system at an incremental time. Okay. Then we add the change with respect to the other time step and we march in time. Okay. We keep on adding the changes with respect to the time and we keep on marching. Okay. And these are the points which becomes the response of the system with respect to the time. Okay. So, here how the response of the system will look like with respect to the time. Okay. So, we start at time 0, okay, when initial displacement and velocity are known. Okay. Most of the time they are assumed to be 0. Okay. Then the time history is divided into discrete intervals. Okay. So, we divide the entire time history, okay, into discrete intervals. Okay. And this del t, okay, depends upon the structural properties, okay, how small we can divide in the time steps. Okay. So, at each step, okay, we compute the new displacement. Okay. Let us say at 0 we knew that we calculated the response at delta t. Okay. Then we will add the change with respect to delta t once more. Okay. So, we will keep on adding the responses due to this small change in the time value, okay, and will progress forward in time until the full response is obtained, okay. So, at each time instance we will be adding the effect of the new time step with respect to the older one and will keep on marching, okay. So, what is the accuracy of this system, okay. So, if we use small time intervals, okay, it will result in higher accuracies, okay. It means that the more we discretize, okay, higher will be the accuracy of the response, okay. So, less time, small step time, the accuracy will be higher, okay. Large time intervals, the accuracy will be lower, okay, because what will be happening is that if we are considering only this time and let us say this time, okay. So, we will know the values at this 2 points, okay, and in the middle we will have to join it somehow, okay, but it might happen is that in the middle there are certain oscillations. So, we will miss those oscillations, okay. So, if you use large time interval, okay, the accuracy will go down, okay. So, this is the accuracy, but if we are using more time interval, okay, the cost of computation will be more, okay, the cost of computation will be more, okay, and if we use large time interval, the cost of computation is less, okay. So, this is always a trade off between the cost of computation, that is the faster computation or slower computation with respect to the accuracy, okay. So, we will have to achieve a middle path where we also do not compromise the accuracy and this is under certain limits and our computation time is also to a value so that we can use the results effectively, okay. So, the comparison of the numerical integration with respect to the design charts, okay. So, unlike design charts, okay, so the design chart provide quick approximations using pre-computed non-dimensional solutions, okay. So, we have seen that in the design charts we will have y dynamic versus y static, okay, for the different resistance versus the loading value, okay, and we will have Tn over Td, okay. So, they will be subjected to specific loading requirements, okay. So, what we can do is that this design charts are already made, okay. So, we can just read the values, okay, and calculate the values, okay, but these are normally based on single degree of freedom approximations, okay. So, the design charts provide quick approximations using pre-computed non-dimensional solutions, okay. So, these are the non-dimensional solutions, okay, and if we put the actual values here, we will get the value of y dynamic or any other response quantity, okay. But in numerical integration, okay, what we can also do is that we can handle any type of load and any resistance functions, okay, even complex non-linear cases, okay. So, here for each loading condition we will have to make a design chart, okay. So, the design chart will be different for each loading condition, okay. So, there has to be n number of design charts, okay. So, they have to be pre-made depending upon the loading condition, okay. But in numerical integration any type of loading can be handled, okay. Here also we can handle any type of loading, but we have to prepare the design chart depending upon that particular type of loading, okay. But in the numerical integration, as we come across any type of loading, we can handle those loading, okay. Also any resistance function, okay, even if we go into the complex nonlinear cases can be handled easily by the numerical integration, whereas here, okay, we will have we do not have all the values of R over P, okay. In addition to that, this is only a single degree of freedom analysis system, okay. Our design charts are primarily based on the single degree of freedom system analysis, whereas in our numerical approximations we can make functions using multiple degree of freedom system also, okay. So, the numerical method is essentially a time stepping simulation of structural motion under blast loading, okay. What it means that it is an step by step augmentation over a time, okay. So, this basically a time marching scheme, okay. This scheme is more flexible, accurate, it is more flexible means that it can handle any type of structure and any type of loading, and it has also the ability to incorporate more degrees of freedom, okay. So, thus the accuracy also increases, but they are computationally heavier, okay, than the design charts. Design charts we can approximate using a single degree of freedom system and we can easily get the values, okay. but if we do using a numerical method, it will take certain amount of time. The modeling of the structure, the modeling of the loading, setting up everything, running it, okay, checking the accuracy, achieving a predetermined accuracy. So it takes a lot of time, okay. So again, there is a parity between the accuracy versus the time required, okay, between the design charts and the numerical integration, okay. So depending upon what type of cases we are handling, in what situation we can choose depending between the design chart method or the numerical method, okay. So we'll look into a simple 2 degree of freedom system, okay. So this is just the 2 degree of freedom system representation, okay. So here we have two masses, okay, mass 1 and mass 2, okay. So mass m1 and mass m2, okay. Each mass can move in 1 degree of freedom, okay. So the total degrees of freedom is 2, okay, as we have learnt earlier, okay. So mass m1 can move horizontally in the horizontal direction, okay, with degrees of freedom considered as x1, and again the mass m2 can move in the horizontal direction and its movement is denoted as x2, okay. A1 and V1 are the associated accelerations and the velocities, okay. F1 is the force applied to the mass m1, F2 is the force applied to the mass f2, okay, and there is a spring k1 and here there is a spring k2, okay. So coordinates x1 and x2 are the degrees of freedom, applied forces are f1 and f2, okay, at each degree of freedom. So the internal resisting force will be provided by the springs R1 and the spring R2, okay, and masses are m1 and m2, okay. So the effect of the damping, so should we consider it or should we not consider it, okay. So there is always a debate on that, so we will look into that, okay. So the effect of damping are hardly ever considered in blast design because of the following reasons, okay. They can be considered, but traditionally they are not considered, okay. Some of the main reasons for that are damping has very little effect on the first peak of response, okay. So the damping has more or less zero effect on the first peak of response, which is usually the only cycle response that is of interest, okay. So normally in blast analysis what we are interested is in the first peak response, okay, and since damping has a very little effect on it, okay, we normally ignore the effect of the damping. The energy dissipated through plastic deformation is much greater than dissipated by the normal structural damping, okay. So as we have seen earlier in the damping, so damping is what? Damping is nothing but a method to calculate all the energy dissipation mechanisms, okay. So the total amount of energy that is dissipated by the normal structural damping, okay, it is very less when we compare to the amount of energy dissipated through the plastic deformation, okay. So in the blast case the plastic deformation occurs, okay. So the magnitude of the energy dissipated by the structural damping is minimal when compared to the plastic deformations, hence this effect of damping can be neglected, okay. So ignoring damping is a conservative approach. What does the conservative approach means, okay. So what is going to happen if there is no damping and if there is a damping? So if there is a damping, if there is no damping in the system will be oscillating, okay, through and through, okay. But if damping is considered, the system is going to die down like this, okay, and the total magnitude will be also a bit less, okay. So if we are ignoring damping, what we are doing is that we are overestimating the response, okay, and when we design it, okay, we will design it for a higher response, okay, which is again a conservative approach, okay. So two things come into picture here. If we ignore the damping, our computation becomes easier, okay, and also if we ignore the damping, we are designing for a overestimated thing, okay. It means that our design becomes conservative, okay. So considering both the scenarios, okay, less time required as well as an conservative design, we also try to ignore the damping in most of the cases, okay. So continuing our problem, the 2 degree of freedom system that we have shown. Okay. So, we can take out the 2 free body diagrams. Okay. So, if you take out the first one, okay. So, first one using D'Alembert's principle, we apply the pseudo acceleration m1 a1 double dot, okay, here using D'Alembert's principle m2 a2, okay, if we are using, okay, m2 a2, okay, then applied load F2, okay, here applied load F1, resistance due to the spring, so it has moved x1, okay, so k1 x1, okay, and here if we are considering this thing, okay, it has, let us say it has moved x2, okay, and if you are considering x2 here, so the net displacement in the system will be x2 minus x1 and the resistance will be k2, okay, and then we write down the equation of motion, okay, for the 2 degrees of freedom system out here, okay. So, here F1 will be there, okay, R2 minus R1, R2 minus R1, which is equated to the total inertial force in the system, okay. For the second body, again the same thing, okay. So, these are the 2 equations of motion, okay. So, this is the free body diagram and this is the equation of motion, okay. So, rearranging we can write in the acceleration forms, okay. So, A2 and A1, okay, can be expressed like this, okay. So, now what we are trying to show here is the numerical integration method, okay. So, we are trying to show the numerical integration method, okay. So, we have wrote our equation in terms of the accelerations, okay, A1 and A2, okay. So, we can use different methods, okay. So, we can use the average acceleration method, okay. So, for each mass, okay, the velocity and displacement, okay, are given by the velocity at previous conditions, okay, acceleration at that condition and acceleration at the previous condition, okay. So, this is what we are trying to do, is that we are trying to march with respect to the time, okay. So, this is the average acceleration method, okay, or equivalently this is the average acceleration method, okay. So, if you remember from our first year, so this is nothing but y equals to y naught plus ut plus half at square, okay. So, this is a similar equation, okay. So, only thing is that what we have done is that we have discretized this thing with respect to the time, okay. We are taking the contribution from the previous time and we are trying to march it, okay. So, here if you look it closely, what we are trying to achieve, okay. Let us say this is time t, this is time t minus 1. So, what we are trying to do is that we are trying to compute the response at x equals to t. So, for doing that, what we are taking is that response at x t minus 1, okay. Then the contribution of the velocity, that is the contribution of the slope times t, and the average acceleration, okay, the acceleration, the average of the acceleration, okay. So, here we are trying to compute this portion, okay. So, this is how we are trying to march in respect to time, okay. So, x t at time t previous value and the incremental value in this time t, okay. So, this is what we known as the average acceleration method. So, using the average acceleration method, we are trying to calculate the value of the responses, okay. So, this is one example of the numerical integration, okay. So, similarly, we can use different type of numerical integration scheme also in order to calculate the marching in time, okay. So, we have seen how to deal with the design charts, we have seen how to do the numerical integration, okay. So, using these 2 methodologies, depending upon the accuracy required and the amount of computational time required, we can employ any of these 2 methods. So, practice these things, we will continue in the next class. Thank you.